Hello everybody, so a big welcome to our CCPBioSim industry talk, and it's my enormous pleasure to introduce Paul Graham and Alan Gray. They're from NVIDIA, and of course they're the people who make the GPUs that make your simulations run really fast. So I'm particularly delighted that Paul and Alan were able to come today, because I think that in our community, with our supercomputing facilities becoming more complicated and more heterogeneous, it's important for us to understand a bit more about why our codes function in particular ways on particular machines. And I'm not an expert on this, so I'm now going to hand over to Paul. Thank you very much, Paul.
Thanks, Sarah. I will just share my screen, and if people don't mind, I'm just going to stop my video just because in case of bandwidth issues. So thanks very much for inviting us to do this. It's a two-part talk. I'm going to talk initially about just a sort of general high-level introduction to GPU programming, and then my colleague Alan is going to do a bit more of a deep dive into looking at GROMACS. So my background is I'm a senior solutions architect with NVIDIA. I used to work at EPCC, which is the supercomputing center at University of Edinburgh. I worked there for many years as a software architect. I joined NVIDIA 2 years ago, and as a solutions architect, my role is to give advice, training, information about how to make best use of our GPUs, which GPUs are suitable for a particular job, and so on. And it's essentially just dissemination and information about our GPUs. So in the first part of today's presentation, I'm going to cover the basics of the GPU. We'll look at why the use of GPUs has risen so much in the last 10 years and the fundamental differences between CPUs and GPUs. Oh, I've jumped on, sorry. We'll look at some of the features of the GPU hardware, and which of those features are worth keeping in mind to ensure you can make the best use of them, even if you're just running pre-baked applications and not directly developing software. This keeps jumping forward. Might be on it. Sorry about that. I don't know why it's jumping forward. I'll cover some of the different ways we can use GPUs via software frameworks, libraries and tools, and then I'll cap off with a look at some of the material available to academics before handing over to Alan. So let's get started. Many of you might already be aware of NVIDIA's relationship with APC and AI, and more generally with the rise of GPU computing. I tell you, just to minimize that. One way, so what we have here is a visualization I think is quite helpful. So one way to think about is what's happened over the last 40 years. So that originally people used to rely heavily on the trends in the lower part of the graph on the right as dictated by Moore's law, which is essentially that CPU and single-threaded performance basically got predictably faster year over year. And so you could rely on a new chipset or a new architecture coming out for single-threaded applications that would allow you to achieve an increase in speed up and make your code run faster. But unfortunately, this trend has plateaued, and we can only really squeeze so much performance now out of a single-threaded instruction set. And you can only make transistors so small. So what's happened in the last 15 or 20 years or so is that we've seen the rise of parallel computing, and more specifically GPU computing, as a paradigm that allows us to get back on this trend of increasing performance year over year as it relates to user applications. The way that is possible is by a combination of using a general processor like a CPU in combination with a massively parallel architecture like a GPU. So on the left here, you take the sections of your code that are really computationally intense and parallelizable, typically a small fraction of the overall code, but by far the most time consuming, and you run those on the GPU, which allows you to, in many cases, achieve orders of magnitude speed up. Let's look at some of the key differences between CPUs and GPUs. As we've seen from the previous graph, the increases in individual thread performance of CPUs has been stalling. And in order to try and counter this, CPUs have moved to an increasingly multi-core architecture, with the latest CPUs having up to 128 cores, all with fast clock speeds. CPUs also have a large main memory. We often see servers now with terabytes of RAM, but the bandwidth of that memory, i.e. how quickly we can move data about, is actually relatively low. CPUs are designed to run multiple different applications at once, such as running an operating system with all the associated services, or running your word processor alongside a browser. Individually, these tasks and applications are essentially serial in nature. So each of these applications is assigned to a single thread or a small number of threads. And these are scheduled in a time-sliced manner to run on the CPU. Then a given thread must get as much as possible accomplished during its own time slice. And this requires low latency, i.e. we want to minimize the delay between issuing a request for data and actually being able to execute the instructions on that data. And this implies large caches to hold the data required by the threads and complex control logic to ensure that the data is ready to go when the thread is running. The consequence of this is that a large amount of the silicon on a CPU is actually dedicated to this movement and prefetching of data, which means that the CPUs have relatively low performance per watt, as a significant proportion of the energy that they use is used just for data movement rather than actual calculations. We contrast that to the GPU, which is optimized for executing highly parallel tasks. And of course, this stems from its roots in generating actual computer graphics, where one can imagine the same operation being applied to millions of pixels multiple times a second in order to render realistic scenes. Modern GPUs have a huge number of compute cores, over 10,000 for some of the latest cards, but these compute cores are much more lightweight. They don't have the complex logic for prefetching data, for example. So instead, the GPU deals with the issue of latency by hiding it with computation. Essentially, we give the GPU much more work to do than there are physical cores to execute it, a very different approach to the CPU. So the scheduler on this GPU launches a thread. That thread tries to execute an operation, such as an addition. If the data is not there ready for the thread to use, it issues a fetch command to memory, and it stalls while waiting for the data to arrive. The scheduler then moves on to another thread to execute its instructions, and so on and so on. And this creates a pipeline of issued instructions across a series of threads. Eventually, of course, the original thread's data is ready, and then it is able to continue execution. So this switching between threads actually hides the latency of the memory fetching and the issuing of instructions. And thus, the more work we can give the GPU to do, the easier it is for the scheduler to hide this latency. So we'd actually need many overlapping concurrent threads. To support this, the GPUs have a very large register file to hold the state of the threads, and actually switching between the threads happens at no time penalty, even as often as every clock cycle. As such, the significant majority of the silicon on GPU can be given over to computation rather than data movement, which is what gives them a very efficient performance per watt. Another difference is that GPUs have very high bandwidth main memory compared to a CPU. And given that many applications are bandwidth bound rather than compute bound, this can also deliver significant performance improvements. The additional bandwidth, though, comes at a cost, with the GPU memory being significantly faster but relatively smaller. For example, the latest generation we have, the largest one we have is an 80 gigabyte memory. However, it runs at a massive 2 terabytes a second. Something else that we need to consider with GPUs is the precision that we want to use for our simulations. Each compute core is actually dedicated to a particular operation, be it integer, single precision, or double precision calculations. So different GPUs may have more or less of these depending on what market they're aimed at. For example, the V100 and the new A100 cards are ideal for double precision calculations, as they have a large amount of the double precision cores. So whether you choose a GPU or CPU depends on what sort of tasks you have. And of course, it's typically the case that applications will have a mix of both serial and parallel, in which case you would use both processes together. Let's look now at a couple of additional hardware features in the GPU, which is, as computational scientists, is good to know about. So first off, we'll look at Tensor Cores. These were first introduced in the Volta generation of cards, and these are hardware units on the GPU dedicated to performing matrix multiply and accumulate, or MMA, operations, and they can perform many of these per clock cycle. They were originally aimed at deep learning applications to support mixed precision calculations. For example, on the V100, the Tensor Cores can take in single precision data, multiply it at half precision, then accumulate it back into single precision. And this happens at a significant speed up over the standard MMA on the normal cores. Then the Turing generation of GPUs, such as the T4 or the RTX 6000, extended the support to additional precisions, such as int8 and int4, which is great for accelerating AI inference, for example. With our latest Ampere architecture, we've introduced the third generation of Tensor Cores with support for even more data types for deep learning, such as bfloat16, but we also have now a full double precision support for the MMA operations, which is particularly used for many scientific applications. If we think about how we utilize GPUs in the higher education environment, workloads will change over time. Sometimes you want to perform complex simulations or visualizations, which will require the use of several GPUs to work in tandem. However, other times you'll want to be able to support multiple researchers doing, for example, development work, or interacting with the GPUs via Jupyter notebooks, or testing and developing software via IDEs, or even the command line. Or you may be running a teaching lab where each student needs a dedicated GPU. To help researchers to handle this wide spectrum of accelerated workloads, the A100 card, which is our latest Ampere card, offers a new feature called MultiInstance GPU, or MIG for short. MIG allows each A100 to be partitioned into as many as 7 individual GPUs. Now, each of those MIG instances has its own dedicated cores for compute, dedicated memory, and dedicated bandwidth to ensure a consistent, high-quality experience for each user. To all intents and purposes, it just looks like a smaller GPU. And the instance sizes are flexible. So you could, for example, create one instance using half the A100 to run, say, a molecular dynamics simulation, while splitting the other half of the GPU into 3 smaller instances to support multiple users doing the development work. And on the A180 gigabyte, the smallest instance still provides 10 gigabytes of the high bandwidth GPU memory. So these are certainly not insignificant resources. If we think about how the GPU works, we have to get data onto the GPU for it to perform its calculations. For a single GPU, that is usually via the PCI Express bus, PCIe Gen 3 for V100, and the new Ampere cards support Gen 4, which effectively doubles the bandwidth. However, PCIe bus is still relatively slow, of the orders of tens of gigabytes per second, compared to the bandwidth on board the GPU itself. So this can be a bottleneck, especially if we're making use of multiple GPUs at the same time. There are a few ways to mitigate this programmatically, for example, by overlapping data transfers with compute, or moving even more of the calculations onto the GPU, even if there's no significant acceleration, as it means the data can be generated on and remain on the GPU. On the hardware side, we have NVLink. This allows the GPUs to access other GPUs' memory within the same node directly without having to go via the PCIe bus. And it supports much higher bandwidths. On Volta, up to 300 gigabytes a second, and Ampere doubles that. In addition, some systems such as the DGX2 or the new DGX A100 come with NV switch, which further increases the bandwidth as the NVLink streams can feed directly into the switch. We also have GPU Direct, which is a software and hardware support for directly accessing GPU memory without going via CPU memory. This started out with GPU Direct peer-to-peer for GPUs within a node, then GPU Direct RDMA, which allows GPUs to access each other's memory across nodes. We now have introduced GPU Direct Storage, which allows the GPUs to get data directly from storage without going via the CPU, which not only speeds things up for the GPU, it also releases cycles for the CPU. And I'll just touch on as well, we're also investing in new data processing units, or DPUs. The idea behind these is to provide a system on a chip architecture with network cards, ARM cores, and ultimately GPU cores for managing the data center infrastructure and networking, storage, and security services, also relieving the CPU of some of its burden. So this is a diagram of DGX1, which is what the JADE system, which hopefully many of you are familiar with, makes use of. So each DGX1 has 8 V100s, and each V100 has 6 NVLinks per GPU, and which are connected in a hybrid cube mesh as displayed on the right. In addition, you'll note that the GPUs can access the network cards directly via the PCIe switches, which again removes a potential bottleneck if they had to go physically via the CPU to communicate with the network cards. Also, I believe a lot of you use the system BEAD, which is based at Durham, and that's slightly different. It's an IBM Power 9 system. And the unique feature of the Power 9 CPU is that rather than connecting to the GPU via the PCIe bus, it can actually connect directly via NVLink. So the CPU to GPU bandwidth is massively increased. So again, this is something to bear in mind when choosing your system. So how do we actually get running with accelerating our software? So most of you probably are familiar with using applications which are already GPU accelerated. They've already been ported to GPU. So you can actually run them pretty seamlessly. You don't have to think too much about what's going on underneath the bonnet. In addition to applications which have already been accelerated, we have a series of frameworks, and I'll mention those later. But if you actually want to program for yourself, you have to start thinking about how you would like to do that. So first way is probably libraries. So we have a variety of libraries which look very much like libraries you'd be already familiar with, such as BLAS. We have directives-based programming, which allows you to put comments in your code, which directs the compiler to say, we would like this part of the code to run in parallel, either on the CPU or the GPU. And then, of course, we go down to actual programming languages itself. And we'll look at a few of these different options. Typically, when users first come to GPUs to make use of the application frameworks, as I've said, so we'll be talking about GROMACS, for example, in a few moments, which Alan works on. In the world of deep learning, we have TensorFlow or PyTorch. But if you develop your own code in the first instance, one might consider using libraries such as BLAST for linear algebra. The good news is that for many commonly used libraries and operations, there are GPU equivalents which can be slotted in as replacements with little effort on behalf of the developer. And here's just an example of a few of the libraries. The key thing I'd like you to take away from this, though, is that we put a huge amount of effort into making sure these libraries are both easy to run, but also can exploit the new features in each generation of hardware. As an example, we mentioned earlier, we have the new third generation of Tensor Cores and the A100 with support for new data types. And we've actually worked on all our libraries so that they can directly support making use of the Tensor Cores without too much effort from the side of the developer. So it really means that you can take advantage of the power of the hardware without having to do too much additional work. If you want to get beyond the libraries, then you have to think about how to program for a GPU directly. And if we look historically, starting at the right, going towards the left, this is a sort of a history of it. Before we had CUDA, which is our way of programming directly for the GPU, people used to try and mimic their physics system or chemical systems they were trying to describe using the kind of language that we use to describe visual effects in games. And this wasn't a very easy way to program. So along came CUDA, and this allowed us to express our code in a way which is much more familiar to HPC programmers. Then we introduced the directive-based program, and of course, as well as directive-based programming, there are extensions to the C++ language or Fortran, which allows you to write code explicitly for the GPU. But what the trend we're moving towards now is we want to actually see code which can run on the GPU, but written just in the standard languages. So no extensions, no directives. And we've actually introduced that now with our latest series of compilers. So on the left there, those two code examples, that's pure C++ at the top and that's pure Fortran at the bottom. And both of those can be compiled to run directly on the GPU with no additional directives and no additional calls to extensions. I think this is a really powerful way to get programmed with the GPUs. So if you were starting to program on the GPU now, I'd probably recommend doing this diagram in reverse. Start on the left, use your standard C++, your standard Fortran, program in the languages that you're familiar with. Then if you want to get a bit more control over what's happening, you perhaps use directives to move the data around. And then finally, for the ultimate in performance, you'd probably want to go down to the direct programming languages such as CUDA. In terms of performance, how do we ensure we're getting the best out of the GPUs? Whether we have a few tools to help with that. I'll just mention a couple of them. So we have the Nsight performance tools. Nsight Systems allows you to analyze applications at the system level. Then when you find a bottleneck you really want to look at, you can look at Nsight Compute, and this allows you to dig down deep into the GPU programming itself. And that's a really useful tool because it gives you a huge amount of insight and advice on where there's potential to improve performance. So you can really optimize your code. At the system level, we have various tools for monitoring your resource usage and making sure you're getting the best use of the GPU. So DCGM is one I've mentioned there, the Data Center GPU Manager. I mentioned earlier platforms and frameworks. So the idea behind these are all targeted at particular fields, and the aim of them is to make it as easy as possible for researchers to develop and deploy their own solutions in a particular arena and minimize time spent reinventing the wheel. So there's links here for all of these, but I'll touch on a few of them. Any text underlined in green, and I may have said this earlier, but I'm going to share these slides afterwards so you can get access to all these. Any text underlined in green is actually a live link. So we have Clara. This is a suite of SDKs and tools to assist in healthcare. These include pre-trained models for image classification and segmentation, AI-assisted annotation for labeling medical scans, the Parabricks software for genome analysis, and BioMegatron, which is a natural language processing neural network model, and that can be used to analyze research literature. SimNet, I think, is a really interesting one. This is one of our newer offerings, and this provides a framework to make use of partial differential equations, along with the boundary and initial conditions to create neural networks informed by the physics, informed by the equations themselves, rather than data, which is the more traditional way of exploiting neural networks. And you can get access to this now via early access programming. Omniverse is a collaborative platform for visualization. This allows complex workflows, such as multiple teams, multiple groups visualizing and interacting with a simulation whilst it's running on a remote system. And I've actually got a demo here of Omniverse in action. So let's just see if this plays. So This is a visualization of COVID-19 spikes in action. This was based on the data generated from the Folding at Home Consortium, which calculates intricate movements of proteins inside the coronavirus. Then a team from NVIDIA combined the best tools from multiple different industries to let the researchers see their data in a whole new way. So this is taking advantage of Omniverse, which is helping us render this using the actual scientific data itself. And it's a huge data set which has been used to render this. It also makes use of the RTX cards, which have support for real-time ray tracing, which is why you can see all the fantastic lighting effects here. But it was very pretty. It's also important to note this allows you to get a real insight from your scientific data. You know, it brings it much more to life and helps you get a much better understanding of what is going on. So I think this is a really nice tool. I'll just let this finish while I take a sip of water. Okay, so just get to the next slide. Okay, so let's look at some of the resources available to assist researchers to get going with GPUs. So many of our frameworks and platforms and much of the HPC software that we provide is available via NGC, which is our repository of containerized software. As well as the major frameworks you'd have for deep learning like TensorFlow and PyTorch. It's worth noting that we have model training scripts to help get started with AI if you're interested in AI, example workflows for various applications such as medical imaging, and various pre-trained models which you can use to retrain for your particular area. So it's a very useful resource. It's all free. To get access to. The main thing I want to mention here is that we are constantly improving the software side of things. So if you are making use of, for example, the major frameworks like TensorFlow, PyTorch, regularly update your version of it with the version from our container, and you'll see all the different optimizations that we've made, and we'll see you keep taking advantage of the fantastic hardware that you've already got. We have the Deep Learning Institute. So this, for those of you interested in a deeper dive into programming for GPUs or for training and deploying AI applications, we have a range of courses which are either self-paced or instructor-led offerings. We also have a University Ambassador Program where interested candidates at higher education institutions can become certified to deliver these courses themselves. We also have developer teaching kits. These can be accessed by lecturers or professors to include in their teaching material. We run various academic workshops. I've mentioned the Ambassador Program already. We have boot camps, which are two-day usually tailored training events, typically for a target group, for example, using OpenACC for doing directives-based programming. And we have a new one called AI for Science, which is an introductory AI course for scientists. And also we run hackathons. So these are great in-depth events where we get access usually to NVIDIA DevTech team, of who Alan is a member. And these allow you to bring along your code and either move it to GPU or improve its performance on GPU over a period of a week. I'll just mention in passing, the GPU Technology Conference is happening in April. It's a virtual event, so easy to attend and free. Lots of interesting talk on some of the technologies and frameworks we've touched on today. And also most of the talks will be recorded, so are searchable and available after the event as well. And just before I finish, last thing I want to share with you, this diagram illustrates what it illustrates is the generational leaps in performance due to the introduction of new hardware, but also the incremental increases in performance via our and the community's improvements to the software stack. So here, this is the performance improvements for a basket of both HPC and deep learning machine learning applications. And as we can see during the lifetime, for example, of the V100 cards, we've seen an over 2x performance increase purely from library improvements and software innovations within the codes themselves. So if the only thing you take away from my section is, if you're using accelerated applications, please keep them up to date so that you can continue to take advantage of all the work which has gone on and continues to go on in making sure they can run as fast as possible. So now I will hand over to